Hello and welcome to the second video on the topic of graphs and transformations. It's chapter 4 again from the algebra book in the year 12 course. So previously we looked at sketching cubics. Today we're going to be looking at sketching quartics. That's where the highest power of a variable is power 4. Before we start looking at that though, what I want you to do as ever is try the warm-up questions first and then use this video to help out if you're not sure where to do or what to do if you get stuck, and also of course use a video to just double check if you've got the questions right or wrong. So try these first, then use this video to just see how you've done. Okay, so let's kick off by looking at question 1. Question 1, we're told to factorise fully this expression here. So the first thing we need to think about is if this first bracket will factorise any further. Can we think of any two numbers which multiply together to give us 6 and add up to -1? Well, actually, I don't think we can we? We could have -2 minus 3 added up to -5, 3 and 2, that adds up to +5, 6 and 1 adds up to 7, or -6 and -1 adds up to -7. So this bit doesn't factorise. This bit, however, does. So we could factorise this because two numbers that multiply to -14 and add to 5 are +7 and -2. So we can rewrite this first bit, this last bit rather, as x plus 7, x minus 2, and then we can leave the first bigger bracket as it is because it doesn't factorise. And that's as far as it will go. So it factorises fully into 3 different brackets. Question 2, we have a sketch. We need to rewrite this function in this form here, where a, b and c are constants. So going back to the previous lesson, what we need to remember is that we can write a cubic in this form. We can write the cubic in the form where we have some factor at the front, in this case it's a, which is given for us, and then the roots. So first root, call it alpha, so minus the first root, x minus the second root, x minus the last root. So we can see here it has 3 roots, so we can substitute these in. So the first root, I'm going to call that alpha, that's going to be -3. The second root, beta, is -1, and the third root, gamma, is +3. And so if we substitute in these numbers, we get a x minus -1, x minus -3 becomes x plus 3, x minus b becomes x minus -1, which is x plus 1, and x minus gamma becomes x minus 3. Now we can see already that we've got x plus 3 on one side, x minus 3 on the other, so this is a difference of 2 squares. So this can be rewritten as a, brackets, x plus 1, then x plus 3, x minus 3, we can put together as x squared minus 9, because this is difference of 2 squares. But we're not quite done, because we need to find what a is. We know it's some constant at the front, so what we need to do is substitute in another point we know. Well, we know the the y-axis intercept is -4.5, and so we can substitute this in. For f of 0 is -4.5. So f of 0 is just a. When x is 0, this becomes 1. When x is 0, this is just -9. And we know that has to be -4.5. 1 times -9 is -9, so we know that -9a must be -4.5. Then dividing through by -9, we see that a must be a half. Therefore, this function of x, therefore f of x must be a, which is a half, x plus b, where b is obviously 1, then x squared plus c, and in this case c is minus 9. Well, that's all we need to do for warm-up question 2. For question 3, using a calculator or otherwise, sketch separately on these axes these graphs. So y equals 1 over x. So a calculator can help you, and I invite you to do so if you need. But essentially, if you divide through by x where x is tiny, 1 divided by something tiny becomes huge. On the other hand, if x becomes massive, 1 divided by something huge goes towards 0. So what we'd have for this one is this sort of shape. On one side, but at the other side, where x is just slightly negative, say minus 0.001, y is going to be very negative indeed. Whereas x is a hugely negative number like minus a million, this is going to be nearly 0, but it's going to be minus a tiny value. So from the other end, we're going to have something a bit like this. And these here, where it gets close to the y-axis and close to the x-axis, they're called asymptotes. So that word is this. It's where a curve becomes infinitesimally close to a straight line without ever actually quite touching it. So the y-axis and the x-axis are asymptotes in this case. As they are for this one, in fact. Y equals 1 over x squared. When x is a positive value, it's very much the same as what we had here. In fact, it's almost exactly the same characteristic shape, in fact. Something like this. However, when x is negative, when we square a negative, it becomes a positive, and so it's going to be the same idea on the other side. There's going to be a line of symmetry in the y-axis for this graph. There's going to be something like this. I'm going up like that. Not the best sketch. As I say, if you want to see what these look like, your best bet is to go on, download the app, or go online, desmos.com. Absolutely fantastic software. Question 4. We have a function, a quadratic function, defined as g of x as such, where k is a constant. Given that g has 2 equal roots, we need to show that this equation holds. Well, the main thing here is we're told that g has 2 equal roots. Now, the implication of that, what this means is that the discriminant of this quadratic must be exactly 0. Remember, how many roots a quadratic has is determined by the discriminant. When the discriminant, which we can use this triangle symbol for, when it's greater than 0, we have 2 different roots. When it's equal to 0 exactly, it has 2 equal roots. When it's less than 0, it has no roots. So equal roots means 1 repeated root, if you like. So just be careful of the wording. We're after just 1 repeated root. So the discriminant is b squared minus 4ac. So we're going to set this equal to 0. What I mean by b is the coefficient of the x term. And so in our case, for b is this k minus 1. What we mean by a is the coefficient of the x squared term, which in this case we can see it's 2. And what we mean by c is the constant term at the end, which is this minus 3 plus k bit at the end of the equation. So all we need to do now is to substitute these in for a, b and c. So k minus 1 all squared minus 4 times 2 times minus 3 plus k, that must all equal 0 exactly. Again, where these values come from, I'll just color code them in case you're unsure in any way. So b is k minus 1, a is 2, and c is minus 3 plus k. So let's neaten this up, expand it all out. So k minus 1 all squared is k squared minus 2k plus 1, and this we can say it's minus 8 lots of minus 3 plus k. A bit more expanding and simplifying. K squared minus 2k plus 1, like we had before. Now minus 8 multiplied by minus 3 gives us positive 24. And minus 8 multiplied by k gives us minus 8k. Final step, collect like terms and simplify. We have k squared minus 2k minus 8k, altogether that's minus 10k. Plus 1 plus 24 is plus 25, and therefore we've proven what we set out to prove. K squared minus 10k plus 25 equals exactly 0. Now part B, hence find the values, or value of k. So for part B, let's just bring it over here. We can take what we had from part A and just continue it on. So what we need to do here is factorise this if we can. Two numbers that multiply together to give us 25, when we add them together give us minus 10. Well, that's minus 5 and minus 5, so actually this factorises into a perfect square. This is the same as saying k minus 5 brackets k minus 5 equals 0. In other words, k minus 5 all squared equals 0. Therefore, if there is only one value of k we're interested in, we're after k being equal to 5. We've therefore finished all the warm-up questions now, and we can move on to the main bit of this session. So today we're going to be looking at sketching quartic graphs. I know here it does say and reciprocal graphs. This lesson is the first of two about sketching graphs. So this lesson we're just going to be looking at quartics, where the highest power of x is a power 4. Next lesson we're going to be looking at these reciprocal ones. So for now we just need to think about what a quartic graph is. I'm going to just go to one side for a second and just remind us of what we know already. So a quadratic graph. Okay, so what does a quadratic graph look like? Okay, quadratic where the highest power of x is a 2, and it's either like this, or if it's an unhappy parabola, has a shape like this. So highest power is 2, it has one turning point. It's got either one maximum or one minimum. Last lesson we had a look at cubics. So what was the characteristic shape of cubics? Well, it's like an S shape. So a positive cubic is like this, and a negative cubic was like that. So just as a quadratic has power 2, that had one turning point, which I'm just going to pop in red. If it's cubic, power 3, 1 less than 3 is 2, and we can see that a cubic can have up to 2 turning points. Now we're looking today at quartics. So if a quadratic has 1 turning point, a cubic can have 2. How many turning points can a quartic have? You may have guessed it, it's going to have up to 3 turning points, 1 less than the highest power of x. And so a quartic can look like this characteristic shape. Okay, where we've got 3 different turning points. 1, 2, and 3. Or if it's a negative coefficient on the x to the power 4, it might look negative and have this sort of form here. But still, we'll have its 3 different turning points. So that's just worth a mention, before we start, just so we know what to expect when we arrive at it, so it's no nasty surprise, so you're not thinking, is this right? This looks a bit weird. If it looks like one of these sorts of shapes, chances are you're on the right lines. So I'm just going to section this off to one side for a moment. Now, without getting into the technicalities of cubics and giving you all these different permutations and combinations of the different types of equations which they'll look like, just try and treat this intuitively as a natural follow-on from the last lesson where we looked at cubics. So use your intuition and understanding of cubics to help you with this quartic stuff. Let's look at question 1. So we have this quartic function defined as such. We need to sketch this graph. Now we can follow a similar sort of strategy as detailed in the last lesson for sketching quartics as we did for sketching cubics. So we can set f of x equal to 0 to find the x-intercepts. So we're essentially just hunting for when this expression here will equal 0. So let's set that equal to 0. So x minus 1, x plus 3, x squared minus 4, set that whole thing equal to 0. However, be careful and spot that we have something here which can factorise further. This is the difference of two squares. So this becomes x minus 1, x plus 3, x plus 2, x minus 2 equal to 0. We can now see what the roots are by just inspecting each of these 4 different brackets in turn. So it's going to have roots where x is 1 from this bracket here. From this bracket here we have minus 3, from this one minus 2, and from this final one when x is 2. We determine the y-intercept, if you remember from before, by chucking in x being equal to 0 and seeing what comes out. We basically just evaluate f of 0. F of 0 would give us minus 1 multiplied by positive 3 multiplied by minus 4, which gives us 12. Now we can use step 3, test large positive and negative values of x, but using this understanding here will help us massively, because if we understand this, we don't, strictly speaking, need to do step 3. What we're going to have here is a highest power of x, which is x to the power 4, and it's going to be x times x times x squared. It's just going to be x to the power 4. It's going to be a positive quartic. If you know it's going to look like this, what you should be able to realise before doing step 3 is when x gets smaller, f of x is going to go towards infinity. And likewise, when f gets large, carrying this going upwards, f of x is also going to go towards infinity. But if you're not comfortable at this stage with that idea, by all means do test the values. So, I don't know, just pick a large value. Let's say f of 1000. What we're expecting is that this to be really high up here, where f of x is huge. But don't take my word for it, try it on a calculator. So we're just going to use this expression here, but substitute 1000 for x. So the first bracket becomes 1000 minus 1. Then we have 1000 plus 3. And finally we're going to have 1000 squared minus 4. So that's roughly 1 times 10 to the 12, okay? So that's absolutely enormous. So we can deduce that as x goes towards infinity, as x gets huge, f of x also gets huge as well. Similarly, if we try this for a very negative value of x, say minus 1000, let's see what that gives us. So if I just go back here and just edit all these to be minus 1000 rather than 1000, To be honest, I'm not sure if that's the quicker way of doing it. Maybe it's best if I just alter it all manually, but never mind. I've started now, so I'll finish this method. That needs to be a minus. That here needs to be a minus. 9.98 times 10 to the 11. So again, that's huge. In fact, it's near to 10 times 10 to the 11, so it's near to 1 times 10 to the 12. So it's almost, weirdly, I wouldn't say symmetrical, but it's the same on the other side when you take it to the extreme as it is on the other extreme value of x. So you can see here that as x goes towards negative infinity, f of x goes towards positive infinity. F of x becomes huge, which is what we predicted here. It goes up at either side as x goes really small or x goes really big. So now we just need to use these roots here to help us. So we've got roots at -3 and -2. It's going to come up and cross the x-axis, sorry, the y-axis I mean to say, at 12. Then comes down again, going through at 1 and 2. So here goes nothing. Here's my attempt at a sketch. So it goes through at -3, comes up through -2, crosses the y-axis at 12, comes down at 1, up again at 2, and up towards infinity. Let's get rid of that little tail there. So as long as we label these on, that should be fine. Obviously my graph is very sort of jagged. I'm not very good at sketching, but the examiner will see my point. So we have -3 here, -2, the y-intercept's at 12, then we have over here 1 and 2. Question 2, sketch the graph of a function g where x is any real number. So this can't factorize anymore. Okay, so this tells us all the roots we need. This is going to come into play where I said use your intuition from the cubic sketching, in particular this idea of a repeated root. So just by inspection, we have roots at x equals 0 for this one here, and over here there's going to be a root where x is equal to 3. This one here, because it's a linear expression in a bracket squared, that denotes a repeated root. So we're going to have a repeated root for this one. And that's going to happen when x is -2. And when x is 0, this whole thing at the front just becomes 0, so it's going to cross through the origin. But importantly as well, if you have a look at this, we're going to have an x squared, and then we're going to multiply that by a -x. This is going to be a negative quartic. So don't draw this as one that's curving upwards at the ends. This is going to be going downwards. So it's going to be one of these sorts of shapes. Very important. So now we know that, we can go ahead and have a go at plotting this graph. Sketching, I mean. So repeated root when x is -2. So the graph's just going to bounce at the x-axis at -2. Okay, and it's then going to come down through the origin, then go back up again through the x-axis at 3. So here goes nothing. Bounce, down, up. So, I'll do a best sketch, but again, as long as it's labelled clearly enough, this will be okay. So a repeated root, tangential to the x-axis at -2, goes through the origin, comes up again where x is equal to 3. Question 3 actually has another couple of ways of doing it. So there's more than one method for this one, but one method I'm going to use now is to use the idea of substitution and simultaneous equations. So we've got this diagram here, and we're told that the function has this particular form, where we need to find a, b and c. So if we just think about it closely enough, we can see, importantly, this graph passes through the origin. Okay, so what we can do first of all, as a suggestion, is substitute in that when x is 0, y is 0. So all we're doing here is just substituting in the fact it goes through the origin. Let's see what that tells us. So y, which is 0, equals 3 times 0 to the power 4, that's just 0. That's 0 because x is 0. B times 0, you've guessed it, is 0. All we're going to be left with is c. So 0 is c. In other words, c is 0. So we can now just focus on finding out what a is and b is. Okay, so now we know that that's equal to 0. We can practically forget about it. So now we can substitute another point. So what I'd suggest we go for next is -1. So when x is -1, y is 0. And we know that because that's one of the roots. So let's see what we can find out by inputting when x is -1. So what we have from this is 0 equals 3 times -1 to the power 4. -1 to the power 4 is just 1, so that's going to give us 3. -1 cubed is -1, so that's going to be -a. b times x is b times -1, so that's going to be -b. So in other words, we have that a plus b equals 3. Now what we're going to do is think about when x is 2, this one over here. Okay, so when x is 2, y is 0. And we know that just by looking at the third and final repeated, albeit root. So what we get over here, just section this out so don't get confused, is 0 equals, well, 3 times 2 to the power 4. 2 to the power 4 is 16. Times that by 3, we get 48. A times 2 cubed is 8a, so 48 plus 8a. Bx is b times 2, which is 2b. So it can be rearranged. So we have 8a plus 2b equals minus 48. Just by subtracting 48 from both sides. What we have now is two equations relating a and b, so we can pair these up and solve them simultaneously. So what I'm going to do is rewrite the 8a plus 2b1 over here, and in fact what I'm going to do, what I've noticed just now, I can half both sides of this equation. So I'm going to call this 4a plus b equals minus 24. Just makes it easier if we half through. So I've got this from here by just halving everything. Then underneath I'm going to write a plus b equals 3. What we can now do is do the top equation, subtract the bottom one. take the bottom from the top, I mean to say. So what we're going to have here, 4a take away a gives us 3a. The b's cancel. We then have negative 27. So therefore, dividing through by 3, we see that a must be minus 9. We can now sub this into the fact that a plus b is 3. So a is now minus 9, so minus 9 plus b equals 3. Add 9 to both sides, we see that b must be 12. So now we've got everything we need. We just need to conclude now clearly to the examiner to say we've solved for a, b and c. We had c here, we worked out a just now, and finally worked out b. So just conclude by saying therefore a equals minus 9, b equals 12, and c was actually just 0. And that's solved question 3. Last but not least, another quartic to sketch. H of x is x squared minus 1 brackets x minus 2 minus x squared. So before sketching, let's just take this and make it slightly simpler to read. So we have h of x. Now what I'm going to do here is rearrange this so that this x squared is positive, because if it factorizes, it'll be easier to see if it factorizes by making this into a more normal looking quadratic form. So I'm going to say that's x squared minus 1, and I'm going to multiply by minus 1 all of this. So if I factorise out a minus 1 and switch the sign of everything here, that's going to give me x squared minus x plus 2. So I can move this minus 1 to the front. So I can have minus x squared minus 1, x squared minus x plus 2. Now this first bracket, I'm hoping you'll notice, is a difference of 2 squares. So it's x plus 1, x minus 1. Whereas this one here doesn't factorise at all. And more than that, it has no roots. If you were to test the discriminant on this one, b squared is minus 1 all squared, which is 1. Minus 4 times 1 times 2, that's minus 8, gives you minus 7. So this has no roots. And so this quartic only has 2 roots from this linear expression and this one. This x squared minus x minus 2 bit doesn't factorise, doesn't have any roots. And so all we actually have here is 2 roots at minus 1 and 1. So roots are x equals minus 1 and x equals 1. We can work out the y-intercept by working out h of 0. Just by chucking in 0 into this, we have 0 squared minus 1, which is just minus 1. 0 take 2 take 0, it's just minus 2. So that gives us 2. And so it's going to have a root here at minus 1, then 1 and 2. It's going to look pretty much like a quadratic. However, because it's a minus x times x times x squared, it's minus x to the power 4, it's going to be bending downwards. So it's not going to look exactly like a negative quadratic, but it does look very similar. But because it's a sketch, you don't need to worry about those tiny little details. The main thing is getting the general shape correct and the intercepts labelled on clearly. And so it's going to be something like this. It is going to be very similar looking to a quadratic, so to sketch it like a quadratic, isn't actually a bad idea. And comes down like so. Always go a bit weird at the end, sorry. So, as long as we label on that this is going to be -1, +1 at the other end, and the y-intercept is 2, and that'll do us. Again, if you want to see what this looks like closely, go on to desmos.com and see for yourselves. So now it's over to you guys. I'd like you to go to page 65 where you'll find exercise 4b and try these questions out on your own. You know the drill by now. Try them yourselves, self-assess using the book's answers at the back. If you're making a mistake, check yourself in the first instance to see where you've gone wrong. If you're still not sure, come and see me. Thanks for listening, and you'll hear from me soon in the next video I do. So bye for now, keep safe, keep well.